Hi, this is a more difficult example from the AMC12 involving angle bisectors. So let's see what we have. In triangle ABC shown, we have AB of 7, BC of 8, CA of 9. AH is an altitude, and we have that BD and CE are angle bisectors intersecting AH at Q and P, and we want to find the length P to Q. Okay, so with all these intersecting lines, this looks a bit complicated. Now I see that we have an altitude AH, so we have two right triangles adjoining, and so we might be able to invoke a Pythagorean relationship to relate these two right triangles. I also see that since we have these two angle bisectors, we could work out the ratio of AD to DC pretty easily. We could also work out AE to EB, but I don't see how that advances the problem, so I don't quite see how calculating AE and EB would necessarily tell us how to find out the length of PQ. So I'm not sure what to do with that. So let's go back to the Pythagorean relationship. It looks like it would be helpful to know BH and HC, and therefore also to know the length AH. So let's try to work that angle. So let's call BH of length x. So CH is 8 minus x. And we could now invoke the Pythagorean relationship to compute AH squared in two ways. So now we know that AH squared is equal to 9 squared minus 8 minus x squared. It's also equal to 7 squared minus x squared. And we can expand this now to solve for x. Squares drop, and this reduces to 16x is equal to 32, from which x is equal to 2. So that looks pretty helpful now. So HB is 2, CH is 6, and I think we're on the right track here because someone went out of their way to construct this problem such that these are integer values, and so that means we're probably on the right track here. Now, since we know these base values, we can quickly calculate AH. AH squared is 7 squared minus 2 squared, that's 45. So AH is root 45, or 3 root 5. So that's a big help. Now, the big key here is we notice that since CE is an angle bisector to the larger triangle, it's also an angle bisector to the right triangle. And the same is true for BD. And that's kind of the key to solving this problem, because we can now use the angle bisector rule to figure out the ratio of AP to PH and also AQ to QH. So let's try to work that out. So from the larger right triangle, we know that the ratio AP is to PH as 9 is to 6. So let's make a little figure to indicate that information. So AH and point P, and these line segments are in the ratio of 9 is to 6. And from the smaller right triangle, we also have that AQ is to QH as 7 is to 2. So let's make another little diagram to indicate that. So Q and AQ is to QH as 7 is to 2. So now it seems like we have enough information to work out what the relative ratio of PQ is, because we know that AP is the relative length of 3/5 of AH, and AQ is the relative length of 7/9 of AH, from which we find then that PQ is just the length of AH times the difference of these relative ratios, 7/9 minus 3/5. That's kind of a complicated fraction. That is 35 over 45 minus 27 over 45. That's 3 root 5. times 8 over 45, or root 5 times 8 over 15. Okay, that looks about right, and that's choice D. So we have a pretty difficult problem here that, if you use the angle bisector rule in sort of 2 steps along with the Pythagorean relationship, it does work out pretty easily. So hopefully that helped, and we'll see you at the next video. Take care. Bye-bye.